Alright, welcome students. This is the supplemental lecture from the snow day that we had about a week ago. In this lecture we will continue where we left off from last Thursday's lecture. And so if you remember on last Thursday's lecture we went through our steps of hypothesis testing for a z-test. And now we do a z-test whenever we have a sample and we want to compare that sample to the overall population. And in that population we have a mean and a standard deviation. And so with our z-test we want to compare, is there some difference between the sample to that overall population. So on Thursday we were working with our scenario with Applebee's, and Applebee's would like to implement a new training program nationwide. But before they go through the expense of actually implementing it at every single organization across the country, they would like to test it out with a sample of newly hired employees. In fact, it's a randomly sampled set of newly hired employees or recent hires. And so they would like to take the results, the performance of those employees in the sample, and compare it to the overall population of all employees who have that old training or the current training program that's in place. If you remember on Thursday, we went through all 6 steps of hypothesis testing, at least as they're laid out in the textbook. We said that there's a 7th step, making a practical decision, that we will get to today as well in this particular lecture. So if you recall, our null hypothesis is that there is no difference in the performance of Applebee's employees between this new program that we're testing and the old training program that the rest of the employees in the population have. Now our research hypothesis is that there is a difference. So we're not saying particularly if performance will increase or decrease, we're just saying there's a difference. And so we're setting up our test to be a two-tailed test. Performance could increase, it could decrease. We just want to know, is there a difference? And we see that with the z-critical values that we calculated. And remember, the critical values is that point on the distribution that if the differences between our means from the sample to the population are great enough, given the measure of variability, that we will say that there is a difference at a greater than chance level. And so we set those cutoffs at plus or minus 1.96. We did our calculation on Thursday and we ended up with a z-statistic of 1.83. If we show that visually with our normal distribution, you'll see our cutoff points with the red vertical bars at a z of 1.96 and a z of negative 1.96. You'll see our test statistic, the z-statistic that we calculated, to be 1.83. And you'll see that that z-statistic falls just short of the critical value in the positive direction. So the shaded regions on the graph represent the areas that are critical regions where we will reject the null hypothesis. So if our z-statistic falls within those 2 shaded regions, then we will say we reject the null. But as we can see, our z of 1.83 does not fall within the shaded region. It does not exceed our critical values. It falls just short of our critical value in the positive direction, so we will fail to reject the null hypothesis. In essence, what we're concluding is that the new and the old training program have the same level of performance. So performance does not appear to have increased at a greater than chance level. In other words, we're saying that the probability of the z-statistic that we calculated, 1.83, happened at a greater than 5% chance. So that was our statistical decision. We still have one more step, step number 7, which is our practical decision. Now our practical decision is what we would actually do in real life or in practice. And so I don't really care so much what you say for your practical decision, as long as you make a decision and then support it with the evidences that you have collected. So in this case, our question is whether or not we should implement this new training. And so certainly one of those pieces of evidence is our hypothesis test, the fact that we failed to reject the null hypothesis. We found that there was no difference between the new and the old training program. However, there are other factors that are important to our decision. One of those factors is the reliability and validity of the measurements themselves. And so we measured performance and it was measured on a 0 to 100 scale, where higher scores meant higher performance, but we really didn't operationally define what performance was, or how it was specifically measured. So we could probably assume that the ratings came from supervisors of the employees. And so if they came from the supervisors, there could be a subjective component to that rating. So supervisors may not actually observe their employees all the time. So if you think about it, supervisors have many employees, and so not always observing their employees. They only see them for a certain portion of the day, and so they don't see all of their activities. And so that may lead to some subjectivity in responding. Additionally, supervisors may have favorite employees that they may rate higher, not because they perform better, but just because they like them more. So another factor might be the assumptions. And so we want to look at them and see how well did we meet each of those assumptions. So if you remember from Thursday, we looked at our 4 assumptions for a Z-test. We actually did a pretty good job. We either could assume or did meet each of those 4 assumptions. And so we might have a certain level of validity, or there might be a certain level of validity when it comes to our statistical decision, that we weren't worried about some of the limitations that come with not meeting our assumptions. Another factor that may be important might be whether or not the savings is greater than the costs. And so even though we didn't find an increase in performance, if this new training is cheaper, if it saves the organization money when it comes to training dollars or payroll, then we may still want to implement the training even though we didn't find a difference between the new and the old training program. Maybe another factor is how technical is the training. If this new training is very technical, then maybe we don't implement it. If it's less technical than the current training, then maybe we consider implementing the new training anyway. And of course, another factor that may be important also is the mission and vision of the organization. So what is it that the organization values? And so if it's Applebee's and they value customer service, and this new training program will increase customer service, even though it may not increase performance, then we may still want to implement this new training, even though we failed to reject the null hypothesis. Even though we found that there was no difference in performance in the two types of training, the new and the old, but if it increases customer service, which we value, which is important to our organization, then we may still implement this new training. So what I'm really trying to say here is that with your practical decision, it doesn't matter to me if you say yes, we should implement, or no, we shouldn't implement. What I'm looking for is what is your argument given the evidences that we have collected. So congratulations, you just finished your first hypothesis test, one of many that you will learn this semester. So just take a moment, pat yourself on the back, and let out a big sigh of relief before you move on to the next slide. So we have completed our first hypothesis test, but we're not quite done yet. Even though we complete our hypothesis test, there are still some additional statistical analyses that we need to conduct. Those additional analyses include the effect size, the confidence interval, and we should probably take a few minutes and talk about statistical power. So let's go ahead and let's begin with the effect size. Now you may have noticed that when we went through the steps for the 7 steps for hypothesis testing, that there were several points in there that we made fairly subjective decisions as researchers. So for instance, we talked about how the researcher decides what alpha is. And so if the researcher is deciding what alpha is, then that alpha cutoff, or our type 1 error rate, is fairly subjective. Additionally, we talked about how the Z statistic is influenced by the sample size. In general, the larger the sample, the higher our Z statistic is going to be, and so the easier it is for us to reject the null hypothesis. So given these two fairly subjective components of a hypothesis testing, it's possible that our statistical significance, or our decision of whether or not to reject or fail to reject the null, may not be that meaningful. So in addition to a hypothesis test, we also want to calculate an effect size. So based on the scenario we had a two-tailed hypothesis test with an alpha of 0.05. And so here is our normal distribution. We have our cutoffs, our critical values at an alpha of 0.025 in each tail. So if you add those together, you get an overall alpha of 0.05. And the corresponding z critical for this cutoff point is 1.96 and negative 1.96. And so if you remember, at an alpha of 0.05, we failed to reject the null hypothesis. We concluded that there was no difference between the new training and the old training because the z statistic that we calculated was 1.83. It did not exceed our critical value of 1.96. And that was in the positive direction because our sample mean had a higher performance level than the overall population mean with the old training. However, if we had set our alpha to be 0.10, our overall alpha at 0.10, a 10% chance for a type 1 error, then with our two-tailed test, we would create two critical regions in the extreme portions of our distribution that accounts for 5% of the population. And so our corresponding critical values for z would be negative 1.65 and 1.65. So if our z statistic that we calculate with the sample that we collect exceeds that critical value of negative or positive 1.65, then we will reject the null hypothesis. Now, assuming everything in our calculation stays the same, our z statistic would still be 1.83. And so as you can see on the slide, that blue vertical line shows us that that z of 1.83 falls within our critical region. So that tells us that our sample mean of 76 when compared to the population mean of 72, given the measure of standard error, occurred at a greater than chance level when we set chance at a type 1 error rate of 10%. So ultimately what we see is that the alpha that the researcher decides on may have an impact on the statistical decision. So before an alpha of 0.05, we failed to reject the null hypothesis. We concluded that the new and the old training were no different from each other. However, if we increase that alpha to 0.10, our statistical decision now is to reject the null hypothesis. It appears that the new training resulted in higher performance than the old training. The hypothesis test results are not only affected by the alphas that are set by the researcher, but it's also affected by the sample size that the researcher selects for the study. So if we want to demonstrate how the sample size affects our z statistic, then we have to look at the formula itself. And so we'll start with the standard error. So if you remember, from Thursday we talked about the standard error being the standard deviation in the population divided by the square root of n. And so if you look at the formula, you see that the standard error is a function of the sample size. Because n is in the denominator, the larger n is, the smaller standard error will become. So based on our Applebee's scenario, we said that the standard deviation in the population with that old training was 12. We then sampled 30 employees and gave them the new training, and so that's our sample size is 30 employees, and so that goes in our denominator. So we'll take 12, we'll divide by the square root of 30, and if you recall from last week, the standard error we got was 2.19. So if we put that into our z statistic, we see that the z statistic is affected by the standard error. Standard error is in the denominator again, and so because it's in the denominator, then the smaller the standard error is, the larger the z statistic is. So based on the numbers that we presented in our scenario, we had our mean with the new training with a performance appraisal rating of 76. The mean of the population with the old training was 72. And our calculated standard error was 2.19. So the resulting z statistic is 1.83. And we see that in this slide as that blue vertical line that represents our z statistic. Now we see that it does not exceed our critical value of 1.96, so it does not fall in our critical region, and so we failed to reject the null hypothesis. We would say that there's no difference in performance between the new and the old training, because it occurs at a greater chance than we're willing to accept for a type 1 error rate. So greater than 5%, or a probability of 0.05. So what if instead of sampling 30 employees and giving them the new training, instead we sampled 1,000 employees? So our standard error formula would still be the same, however our numbers would be slightly different. So our standard deviation of population is still 12, however now we're dividing by the square root of 1,000, or the 1,000 employees that received the new training. And so when we run the calculation, we end up with a standard error of 0.38. And so notice that this is quite a bit different than the standard error that we had before. Before it was 2.19, and now we've reduced it down to 0.38. Again, here is our z-statistic formula, and as we mentioned before, that if we're looking at our standard error, because it's in the denominator, the smaller our standard error is, the larger our z-statistic is going to be. So if we plug in those values again, our mean of 76 for the sample minus our mean of the population of 72, but now we're going to divide by 0.38. So when we do the calculations, we see that our z-statistic is now 10.53. That is drastically higher than it was before when we only sampled 30 employees. And in fact, our statistical decision has changed. So before, we failed to reject the null hypothesis. We said that there was no difference between the new and the old training programs. But now, if we had sampled 1,000 employees and gave them that new training program, assuming the mean stays the same for that sample, our z-statistic would increase to 10.53. It would fall within our critical region, and we would reject the null hypothesis. In other words, we would say that there is a difference between the new and the old training programs. In particular, we could say that the new training program results in higher performance than the old training program. And that's because we had a larger sample size. So if our statistical result, our statistical decision, is affected by subjective components such as the alphas and the sample size, which are both under the control of the researcher, then we need another measure, a less biased measure. And that measure is going to be the effect size. As you might expect, the effect size is not affected by alphas nor sample sizes. Because it's not affected by the sample size, the effect size is based in a population distribution of scores. And so when we say a distribution of scores, what we're talking about is that the distribution is made up of individual employees. So no longer groups, no longer samples, no longer means of groups, but rather the individual scores for each one of the employees' performance level. So if we look at our formula, we have the symbol D, that stands for Cohen's D, and in our formula we will take the mean of our sample, we will subtract the mean in the population, and then divide by the standard deviation. And so again, note, we're using standard deviation now, we're not using standard error. And so that tells us a result at the individual level rather than the group level. You will also notice that with the formula that it's not much different than our z-statistic formula. The only thing that has changed is that denominator. It is no longer standard error, it is now standard deviation. But we'll call this the effect size. We'll call this D, which is the symbol for Cohen's D, or Cohen's effect size. If we plug in the numbers from our scenario, so we put our mean of our sample of 76, we subtract the performance rating mean of the population, it's 72, and we divide by 12, then we'll get our effect size. So remember, 12 was our standard deviation. We end up with an effect size of 0.33. Of course, that's just a number, so what does 0.33 represent? Well, in this case, 0.33 is the effect size, and it represents the shift in the population distribution of scores. And so you'll notice on the screen here that we have two population distribution of scores. We have one for the current training program, or the old training program, that's in blue, and then another for the new training program, that is in red. And so the effect size gives us a difference between the new and the training program, not in raw scores, not in performance ratings, but rather in terms of variability, in this case in standard deviations. So we're saying there's a shift with this new training, a population shift of 1/3 of a standard deviation. If we were to write this out, which you'll be asked to do on worksheets and on the exam, then we would say that we can expect on average that any individual Applebee's employees, and remember it's the individual employee because it's on a distribution of scores, so any individual Applebee's employee's performance will increase with the new training by 0.33 of a standard deviation over the old training program. We would call this a small effect. Now we'll come back to categorizing our effect sizes as small, medium, and large in a minute. But first I just want to make sure that we understand what is included in our explanation of an effect size. So when explaining an effect size, there are 6 things that you need to include in your statement. You need to specify that it's at the individual level. So with a hypothesis test, the hypothesis test results, whether we reject or fail to reject the null hypothesis, is at the group level. The effect size, however, is at the individual level. So we also want to identify who or what is being measured. So in this case, we're talking about Applebee's employees. We also want to identify the measurement that is being used. In this case, we are measuring performance. We also want to identify our populations or the groups, so in this case the new and the old training programs. We would like to include the difference in terms of the standard deviations, so that number you calculate. This standard deviation should represent the shift, so you should talk about that standard deviation as saying that one group is higher than the other group, or one group is lower than the other group in terms of that standard deviation. Then finally include the size of the effect. Is it small? Is it medium? Or is it large? To determine whether effect sizes are small, medium, or large, Cohen gave us some conventions for us to follow. In other words, some rules of thumb of how to categorize effect sizes. So if our effect size is around 0.2, we'll say that it is small. If it's around 0.5, we'll say it's medium. And if it's around 0.8, we'll say it's large. And so whether it's small, medium, or large will depend a lot on the context itself, but in the behavioral sciences, we tend to use these particular 3 rules of thumb to categorize effect sizes. So when you're looking at your effect size, calculate the category that is closest to your effect size. So they're not cutoffs. Go with the one that is closest to. So in this case, if we had 0.33, well, 0.33 is closer to 0.2 than it is to 0.5. And so we would say that this is a small effect. But what's most important is that our effect size now allows us to make meaningful predictions. And so this is something that we won't do in this class, but if you were to continue in statistics, we can then go on and do something that's called utility analysis. We can take our effect size and estimate the amount of savings an organization might have given a particular intervention. Or if it has to do with behaviors, we can get an estimate of how behaviors would change for a particular group based on the individual effect sizes. So in conclusion, the effect size gives us a less biased estimate of the differences between our 2 populations. So it provides additional information that can help us make decisions. However, they don't replace the hypothesis test results. So we don't have a preference for the effect size over the hypothesis test, nor the hypothesis test over the effect size. There are 2 different measures that provide us with additional information that helps us make informed decisions. So we always want to consider both rather than just one or the other. We happen to like the probability aspect of hypothesis testing, and we also like the fact that effect size are not affected by alphas or by the sample size. So we've talked about the effect size, so let's move on. Let's talk about the confidence interval. So the confidence interval is an estimate of where we expect the true population mean to fall given our measure of variability and the mean of our sample. So when we collect a sample, we calculate the sample mean as an estimate, a stand-in or a proxy for the population mean. So remember, the whole purpose of sampling is to infer back to the population, and we hope that when we sample that we do so in such a way that it represents the larger population that we wish to infer to. But because the sample is an estimate, it's our best guess of what the population mean is, that because of that, the sample and the population mean are not likely to be the same. And so what we would like to do is create an estimate or an estimated range of where we might expect that population mean to fall. And so that range of our estimate for that population mean has to be at some level of confidence. In other words, a confidence interval. So the data we collected showed that the population performance with the new training is estimated to be 76 based on our sample. However, we already know that our sample mean is not the true population mean of all employees. It's our estimate. It's our best guess. And so what we want to do in this particular scenario is estimate the range of where we would expect the true population mean to be for this new training. So if we were to implement it nationwide to all of our Applebee's employees, where could we expect the true population performance mean to fall with this new training will depend upon that range that we estimate. And of course, when we estimate this range, we want to indicate at what level of chance that this population mean might fall within this particular range, and that's our level of confidence. So to calculate a confidence interval, we need a few things. We need to know our alpha. We also need to know the associated z critical values with that alpha. We need to know our sample mean, and we need to know our standard error. And so there I give you the two formulas. We have an upper bound and a lower bound. So it's a range, and so we need to get a low value and a high value of this range of where we expect that true population mean to fall. Now I've left a couple notes there just so that just to remind me of a couple things I need to talk about. So first of all, confidence intervals are always two-tailed. And so we talked about our hypothesis tests on Thursday, that they can be either one or two-tailed, but our confidence interval will always be two-tailed. And the reason why is that we want to create a range around the sample mean. So if a sample mean is our best guess, it's the estimate for the population mean, then we could be wrong. Our sample mean may be higher than the true population mean, or it may be lower than the true population mean. And so we need to set critical values in both tails of our distribution in both directions. So when we have our sample mean, we're going to create a normal distribution centered at that sample mean. So here is our normal distribution. You'll notice that the properties of this normal distribution are exactly the same as it's been all semester that you've learned. So it's divided up by standard deviations, or what we call z-scores. But now it's centered at the sample mean of a performance appraisal rating of 76, rather than at the population mean of 72. So this distribution represents the performance of those employees with the new training, rather than the performance of employees with the old training. So again, it's now centered at the sample mean, not the population mean. So if we take our distribution and we put in our critical values, so again we use the same alpha that's in our scenario. So we said we had an alpha of 0.05. We said that confidence intervals are always two-tailed, so we need to divide that alpha by 2 and come up with the associated z critical values. And so because it's a two-tailed test with an alpha of 0.05, our z criticals are going to be the same as it was with our hypothesis test. So in this case, negative 1.96 and 1.96. Now it's important to note that if you did a one-tailed hypothesis test, so if our scenario suggested that performance would only increase or only decrease based on previous research, then we would need to calculate new critical values. If our hypothesis test is a one-tailed test and our confidence intervals are always two-tailed tests, then we need to go back and we need to get new critical values for our confidence interval. But in our particular example, we had a two-tailed test hypothesis test. and we have a confidence interval, that's always going to use 2 tails. So in this case, our z critical values remain the same. They did not change. So if you remember from our scenario, when we were calculating our test statistic, that the mean of the sample was 76, and so that is where we will center our confidence interval. So let's go ahead and let's put in those numbers from our scenario to go ahead and get our confidence interval for our Applebee's example. So we'll see here that we had an alpha of 0.05, that the associated z critical values for 2 tails is plus or minus 1.96. Our sample mean is 76 and our standard error is 2.19. So we can go ahead and plug those numbers into our 2 formulas to get the upper and the lower bound of our range. Now it's important to note here that when we say negative z critical in our formula, in z critical, so for the lower bound we say negative z critical and the upper bound we say z critical, what we're talking about is the positive and negative value of the z critical. Sometimes I'll see students put in the z statistic that they calculated for the hypothesis test. That would be incorrect. We want the critical values. Sometimes also I see students put in the negative z critical, and so they end up with a negative and a negative z critical, and they make it a positive z critical, and then their upper and their lower bound is the same number. So just remember that negative z critical is just the negative critical value. For the upper bound, the positive z critical is just a positive z critical value. So if we were to put in the numbers for the lower bound, so m sub lower, we would say it equals negative 1.96 times 2.19 plus 76. The upper bound of our interval would be 1.96 times 2.19 plus 76. And then we can calculate our range for our confidence interval. We end up getting 71.71 from our lower bound and 80.28 for our upper bound. And so what we're saying is that the true population mean for this new training, for performance with this new training, will fall somewhere between 71.71 and 80.29 performance ratings. If we were to write this out, which I will ask you to do, we need to include a few things. The first thing we need to include is the percent chance. Now the percent chance is based on your alpha. So in this particular case, we had an alpha of 0.05. So that was a 5% chance for a type 1 error. So if we take 100%, our entire distribution, subtract our 5% chance for a type 1 error, we get a 95% chance. And so that becomes our level of chance for our confidence interval. So an alpha of 0.05 will be a 95% chance. An alpha of 0.10 would be a 90% chance. An alpha of 0.01 would be a 99% chance. And so we always want to include the level of chance when explaining our confidence interval. So we might say that there is a 95% chance that the true population mean, and we want to say that, we want to say we're looking for that population mean. So there's a 95% chance that the true population mean for Applebee's employees performance for the new training will fall between 71.71 and 80.29 performance appraisal scores. So just like all of our other descriptions that we need to write, we want to include who or what's being measured, in this case Applebee's employees. We want to include what's being measured, we're talking about performance. We want to talk about the group that is based on our sample, so in this case those with the new training. We want to include our percent chance, and we want to include that we're looking for the population mean. So if we were going to write it in APA format, we'll see that in orange at the bottom of the slide. We'll say 95% CI, we'll give a bracket, we'll say 71.71, comma, 80.29, and we'll close the bracket. So essentially what that's saying, that there's a 95% chance that the true population mean for Applebee's employees, their performance for this new training will fall somewhere between those two performance appraisal scores. And so you should also recognize that when we have a confidence interval, and you should include this in your description as well, is that we're talking about the raw scores that we originally collected. So we're talking about performance ratings here. We're not talking about z statistics. We're not talking about standard deviations. We're talking about performance appraisal scores. So again, our best guess for the true population mean was the average of our sample. That was 76. However, we knew that our sample mean was not going to be the population mean, but the population mean should be around that sample mean, and so we create this range of where we expect that true population mean to fall. It could be as low as 71.71 or as high as 80.29, and that's with a 95% confidence or at a 95% chance. And that's your confidence interval. So we've talked about the effect size, we talked about the confidence interval. There's only one last thing to talk about before we can move on to our next hypothesis test, and that's statistical power. So power is the probability of correctly rejecting the null hypothesis. In other words, in saying that there is a difference between our two populations. So in this case, between our new training and our old training. So we want to reject the null hypothesis. We want to increase the probability of correctly rejecting that null hypothesis. And so we call that power. The more power I have, the more likely I am to correctly reject the null. So the proportion of the comparison distribution that's in the critical region is what power represents. And so if we were to draw both distributions, one for each of our groups, so one for our old training and one for our new training, and we were to overlap them, we would want to calculate the percent of the population based on the new training that would fall within the critical region of the old training. And the more of that distribution of the new training that falls within that critical region, the more power we would have. So we don't need to calculate power in this particular class. We could do it with a z-test. However, it becomes a lot harder with the other tests that we learn. And so there's no point, at least in my opinion, to spend the time calculating power for one test, but then not do it for the other test, because the other test would require computer software and we couldn't do it by hand. So we'll just talk about conceptually what power is and how we can increase power. And actually, we've talked about these before. We've talked about these with the hypothesis test, and so I don't think any of this is going to be new, but we'll just reiterate it for each of these three different ways that we can increase power. So the first way that we can increase power is by increasing the alpha. So in other words, if I increase my chance for a type 1 error, then I'll make it easier for me to reject the null hypothesis. And we demonstrated this earlier. We demonstrated this on Thursday, that if I increase my alpha from 0.05 to 0.10, in other words, increasing my chance for a type 1 error from 5% to 10%, then I move my z critical value closer to the mean. And if I move it closer to the mean, then it becomes easier for me to reject the null hypothesis. I don't need as much of a difference between the sample mean and the population mean for me to reject the null hypothesis. Now the problem with doing that is that if I move that z critical closer to the mean, or to a z-score of 0, to the average, then I increase the risk of a type 1 error. So in other words, I increase the chance that I'm going to be wrong when I reject the null hypothesis. So if I increase my alpha from 0.05 to 0.10, I am doubling my chance for an error. I'm going from 5% chance for an error to a 10% chance for an error. So that's not ideal. So increasing the alpha is not the best way to increase our power, and it's the least desirable of our three. The second method is by using a one-tailed test. So what's nice about a one-tailed test, as opposed to increasing alpha, is that we leave the type 1 error rate, or the risk associated for an error, we leave that the same. So that doesn't change. So all we do with calculating a one-tailed test is we move the probability from the other tail. So if I have a two-tailed test, I have two critical regions. I move the probability from one of those tails to the other tail. And so that moves my critical value closer to the mean. However, it keeps my error rate the same. My chance for an error stays the same. Now that's not the most preferred method either, although it is better than just increasing alpha, but it's not the most preferred method either, because even though my type 1 error rate stays the same, my chance for an error stays the same, my test becomes less conservative, because again I'm moving that z statistic closer to the mean, making it easier for me to reject the null hypothesis, making it closer, making the difference between my sample mean and my population mean not having to be so great. And so that's not preferred either. We want to have a conservative test, and we want to keep our alpha at the same rate. And the only way to do that is through this third point, or the third way to increase power, and that's by increasing the sample size. And so we talked about that a little bit earlier in our slide, that if we can increase our sample size, then we can reduce the standard error, we can reduce the fact that people are different from each other, we can minimize individual differences, reduce the variability, increase reliability, and give ourselves a better chance for validity. So in the process, we are increasing power. What's nice about increasing sample sizes is that our alpha stays the same, and our z critical value isn't affected, and so it doesn't move closer to the mean, it stays the same. It's just our population distribution of means are now getting narrower. So it is the preferred method. But remember, as we talked about before, there's some limit to increasing sample size. That if we increase it too much, we reduce the meaningfulness of our hypothesis test, which is why we get an effect size. And so, of the three, if we want to increase our chances for rejecting the null hypothesis, if we want to increase our chances for finding a difference between our populations, the best way to do it, of the three, is increase the sample size. But like we mentioned also, too much of a good thing isn't good either, and so we have that other measure, the effect size, and a less biased measure, to make sure that there's some meaningful differences between our two populations. So when it comes to power, you should know the three different ways of increasing power. You should know which ones are preferred over the others, so know their strengths and their weaknesses. And you should be in pretty good shape if you know those things when it comes to the multiple choice on the exam. So now that we've talked about these additional analyses, let's go back to our practical decision. So now not only do we have a hypothesis test, we have some additional insights that might affect our decision, but now we have some additional calculations, in particular the effect size. So let's talk about what you should include when making a practical decision, especially for a worksheet or for an exam. So when you're making a practical decision, I want you to provide a decision. So in this particular case, we're asking, should Applebee's implement the new training program based on the sample? And so you need to decide whether that's yes or no. And so I'm looking for you to make a decision, to stand on a table and say, we will or we won't implement this new training program. And it doesn't matter to me what your decision is. You can say yes, you can say no, I don't really care. What I'm looking for is your argument for why you said yes or why you said no. And so in your argument, you need to support your answer with at least two statistical evidences. So in other words, you can talk about your hypothesis test, you can talk about your effect size, or you can talk about the reliability and validity of your variables. So two of those three would be just fine. Now when you talk about them, don't just say that our variable was reliable. That doesn't really tell me that you know what reliable means. So make sure you explain why you think or don't think the variable is reliable. Same thing that goes for your hypothesis test. Don't just say that you reject the null hypothesis or you fail to reject the null hypothesis. Tell me what that means. So if you reject the null hypothesis in this case, we're saying that our performance for the new training was greater than the performance for the old training. If we fail to reject the null hypothesis, then we're saying there's no difference in the training when it comes to performance. So tell me not only if you reject or fail to reject, but tell me or show me that you know what that means. And the same thing with the effect size. So just don't tell me that we had a small effect, but tell me what that means at the individual level. So in addition to your two statistical evidences, I would like you to add an additional insight. Something else that may matter to the decision of whether or not, in this case, if we implement this new training. And so maybe you talk about the cost versus the savings of this new training program, and that might be important to your decision. Maybe you talk about the mission and vision of Applebee's, or what you might think that is and how it might relate to a decision of whether or not you implement this new training program or not. And so you're given quite a bit of creative freedom with this additional insight portion. So whatever else you think might matter, talk about it and support it in a way that supports your decision that you make when making your practical decision. And if you do that, then you'll do well on the practical decision on the exam. So those are the three things that I'm looking for. And again, I'm looking for your argument. I'm not so much looking for your decision. I want you to make a decision, but then provide a good argument as well. So with that, we have concluded everything that we need to talk about for a Z test. So now it's time to move on to our next hypothesis test, the single sample t-test. Now what's great about the single sample t-test is that it's pretty much identical to a Z-test except for one major principle or one major concept. And so the single sample t-test is going to feel like a review except for this one change, which we'll talk about today. And the reason why I want to talk about today, and I want to get to this particular aspect of the single sample t-test, is because you're going to conduct a single sample t-test in lab on Monday, and then when we come on Tuesday, we'll go through the hypothesis test from start to finish for a single sample t-test. So let's get the basic concepts out of the way. That way when we come in on Monday and Tuesday, we can just get right down to work and do our hypothesis test. And you'll find that the test the second time around is going to go a lot faster because, again, it's very similar to a Z-test. So before we really begin, we needed to define what's the difference between a Z-test and a t-test. And so here on this slide, you'll see that the assumptions for a Z-test are that the dependent variable is scale, that participants are randomly selected, and that the population is normally distributed. Finally, there is an assumption that we have the parameters for one of the populations. So in other words, we have the mean and the standard deviation for one of the populations. The difference between a single sample t-test and a Z-test is that last assumption. It's the parameters for one of the populations. So in a Z-test, you have both the mean and the standard deviation. But with a t-test, all you have available to you is the population mean. So note that that population mean may be given, or you may need to calculate it. So if you can calculate the population mean, then you have the population mean. Sometimes I have students who are given a set of data and they don't think they're given the population mean because it's just not given to them saying the population mean is X. They don't realize that they can calculate that population mean, and that's the same thing as being given the population mean. So whether we're giving it to it outright or you have to calculate it, if all we have is a population mean, we don't have a standard deviation, then we need to conduct a single sample t-test. So again, we're comparing a single sample, one sample, to the overall population, but now all we have is a population mean. We don't have a standard deviation. We actually see this a lot in practice when it comes to census data. Census data is great for giving us means, but they never include standard deviations. And so we have a population average to compare to, but we have no measure of variability. So with a t-test, what we're going to do is we're going to estimate that standard deviation based on the sample. So remember, when we sample, we want to infer back to the population. So if we get a standard deviation for a sample, then we can infer that back to the population. However, there is a formula problem with the formula that you've learned so far for a standard deviation. So before we can do a t-test, we need to correct for that problem in the formula that we've learned thus far. And so we need to make adjustment to our standard deviation formula. Okay, so the particular problem is that our measure of variability, so in this case sigma for the population, is on a theoretical normal distribution. Now this theoretical normal distribution is an infinite distribution. So if you remember, when we have the normal distribution, it never touches the x-axis. So that x-axis ranges from negative infinity all the way to infinity, and that's at a theoretical level. So in theory, it never touches that x-axis, and so it continues for infinity. However, the sample variability is not infinite. It is finite. There is a low number in our sample, there is a high number in our sample, and and we can't get below or higher than those numbers. And so there's cutoffs. It's constrained, whereas the distribution in the population, the theoretical distribution, is infinite. So the best way to illustrate this is to look at the range. And so the range is a measure of variability. So in a population, as we just mentioned, the range goes from negative infinity all the way to infinity. And so the range is infinite in the population. So here we have a normal distribution. Again, as I was mentioning before, you see that the distribution does not touch the x-axis. It asymptotes on that x-axis. It gets closer and closer and closer, but it never ever touches it. And so the range on that x-axis goes from negative infinity all the way to positive infinity. It never ends. However, for a sample, that range is finite. So if I was to put a sample distribution and overlay it with my population distribution, I would see that the sample distribution will touch the x-axis because we account for every single value in the sample. And so maybe I have a sample, just for an example, I have a sample that has a low score of 4 and a high score of 25, and all the remaining scores or values are someplace in between. And notice that they're more frequent towards the center and less frequent towards the tails. But you can see that the sample is constrained between the two values of 4 and 25, where they touch the x-axis. There's no values below 4 and there's no values above 25. And so when we compare that to the overall population distribution that is infinite, that doesn't touch that x-axis, we find that the measure of variability, in this case the range, is less than the population measure of variability, or the population range. Population range is infinite, the sample range is finite. So if we want our sample to better represent the population, then we need to increase the variability. In other words, we need to increase the range of our distribution. Now remember, there's several measures of variability. In fact, there's 3 we've talked about. We've talked about range, we've talked about variance, and we talked about standard deviation. But it's easier to demonstrate it with range, and so that's what we're talking about here. But regardless of the measure of variability, we need to increase that variability so it better represents the population distribution. So again, the population distribution in this case, the range is the population variability, the range is infinite, and in the sample's case it is finite. And so we need to increase, or we need to change our finite sample distribution, turn it into an infinite population distribution so that we get a better representation when we infer from the sample to the population. So here's our measure for standard deviation. So again, standard deviation is a measure of variability, and it's on our theoretical normal distribution. And again, this distribution is infinite. And so this is the formula that we're used to, and so you'll notice that in the denominator we're dividing by, in this case, the population size, or n, the number of observations in our population. And so this is for an infinite distribution. So again, the problem is that our sample is finite. It has a finite variability, and so we need to somehow increase that variability. And so here is our formula for estimating a population standard deviation from a sample. So you'll notice that our symbol is no longer sigma, it is now S. So S is a Latin Roman letter. It signifies that we are using a sample to estimate the population standard deviation. And so if you look at the formula, it's pretty much the same as the standard deviation formula for the population, except for one difference. We're now dividing by a different number. So instead of dividing by the population size, or n, the number of values in the population, we're now going to divide by n minus 1, or the number of observations in our sample minus 1. So we're going to subtract 1 from the number of observations in our calculations. And when we do that, we turn a finite distribution based on our sample into an infinite distribution that's estimated to the population. So always remember that the sample variability is always less than the population variability. And so if I want to estimate from my sample and infer back to that population, then I need to increase the variability. And I'm going to do that by subtracting 1 from n, or from the number of observations in my sample. So we call n minus 1 the degrees of freedom. The degrees of freedom is the number of scores that are free to vary when estimating a population from a sample. So in a sample we have a set of numbers. Well, those numbers can either be free to vary or not free to vary. So why is it in our formula that we subtract 1? And what does it mean to be free to vary? I think the best way to demonstrate this is to use a problem or an example. So let's say that we have a sample of 3 values. So our n equals 3. And let's say the mean of these 3 values is 5. So what are the values of the 3 numbers? We know there's 3 of them. We know the average is 5. So what is the value of our 3 numbers? So if you said that there are multiple combinations that would meet our criteria of our problem, so in other words, multiple combinations of numbers that would give us a mean of 5 with 3 values, then you would be correct. In fact, there are an infinite number of solutions. So just as long as those 3 numbers average out to be 5, we can have an infinite number of values that could represent our particular problem when we have a sample of 3 that has an average of 5. So for example, our 3 numbers could be 6, 5, and 4. The average of those 3 numbers is 5, and so that meets the criteria of our problem. But also, the numbers negative 20, 7, and 28 would also meet that criteria. The average of those 3 numbers is also 5. We could also use the numbers of 1,212, negative 100, and negative 1,097, and that would still meet our criteria. The average of those 3 numbers is again 5. And so there's an infinite number of solutions to this particular problem. Just as long as the average is 5, we can have any 3 numbers that exist. And so there's no shortage of solutions. So let's adjust the problem just a little bit. So we'll still say we have 3 numbers, and we'll still say the average is 5, except now we're going to put one of those numbers in there. So let's say, instead of having 3 question marks, let's say that one of those numbers is 6. So then what are the values of the last 2 numbers in this sample? Again, if you said that there are multiple solutions, then you would be correct. In this case, there is still an infinite number of solutions that would solve this particular problem. And again, just as long as the average of these 3 numbers is still 5, then we would meet the criteria for our problem. So for example, if we had the numbers 7 and 2, then 6, 7, and 2 would still give us a mean of 5. Also, if we had 1,000,009 and negative 1,000,000, we would still meet the criteria, because 6, 1,000,009, and negative 1,000,000 would still equal an average of 5. And so again, there's still an infinite number of solutions that meet this particular criteria. So let's adjust our problem just a little bit more. And so again, we'll still use our sample size of 3, and we'll still have our mean of 5, except now let's give 2 of the numbers. And so in this case, instead of just having a 6, we'll also uncover another number. We'll say it's 5. And so I have 6 and I have 5, and then I have this question mark. So what is the value of that last number, or that 3rd number? Well, if you said the answer is 4, then you would be correct. And so the next question would be, could that last number be anything else? Could it be anything else other than 4? If you said no, then you would be correct again. It can only be 4. It can't be any other number but 4, because we have to meet the criteria of the average equaling 5. And so for us, for the average to equal 5, then our three numbers must add up to 15. So 15 divided by 3 is 5. And so if I know that I have a 6 and a 5, in order to get 15, I have to have a 4. And it can't be any other number. So in other words, that last number is not free to vary. It is a finite number. It is not an infinite number. And so that's where we get our degrees of freedom. And that's why we subtract 1. We don't subtract 2. We don't subtract 0.5. We don't subtract 1.5. The reason why we subtract 1 is because for any particular sample or any given data set that we get an average for, every observation in that sample is free to vary infinitely except for one of those values. So if I have a sample of 5 and I know 4 of those numbers, then I know what that last number is going to be. It can't be anything else. It's a finite number. So if my number of observations in my sample is 5, then 4 numbers are free to vary infinitely, and 1 number is finite. It is not free to vary. If my sample size is 10, then I have 9 numbers that are free to vary infinitely, and only 1 number that is not free to vary, that very last number. And so when we talk about degrees of freedom, the reason why we subtract 1 is because we're trying to remove that finite number. So theoretically, if I remove that finite number, then I am left with just infinite numbers. And so in my sample, if my numbers in my sample can be anything, if they're infinite, they vary infinitely, then my distribution by necessity must be infinite also. All values in my sample would be possible, and that would create an infinite distribution. So, our degrees of freedom tells us that in every sample there is one finite value. The rest of the values are infinite values. They can vary infinitely. So if I want to convert a finite distribution to an infinite distribution, I have to remove that one finite value from the sample. Now this is theoretical, of course. We can't really do it in practice, but theoretically, if I subtract 1 from my number of observations in the sample, and that one number is the finite number, then I'm left with just infinite numbers. And so my distribution will now be infinite because all values are possible within my sample. So once we remove that one finite number, the remaining values are free to vary, which is our definition of degrees of freedom. So the degrees of freedom is the number of scores that are free to vary when estimating a population from a sample. So in other words, in any sample there is one finite number, one number that is not free to vary. We're going to remove that number from the data set, at least theoretically. And so we'll subtract that one number out and we're left with just infinite numbers, or numbers that are free to vary infinitely. So because we're using a t-test, because we're estimating the population distribution from the sample distribution, then we can't use our z-distribution anymore. And so now we have to use what's called a t-distribution. So our t-distribution goes with our t-tests. The z-distribution goes with our z-tests, or with z-scores. And so I won't go over the t-distribution here in this lecture, but on Tuesday we will go to that table and we will practice with it and make sure that we can get critical values based on the t-distribution that is in your book. And so just as a reminder, here's the formula that we're going to use. This is essentially the only difference between a z-test and a single sample t-test, is the fact that we're estimating the standard deviation in the population. And to estimate that standard deviation, we are going to subtract 1 from the number of observations in our sample. And again, when we do that, we change our finite sample distribution into an estimate of an infinite population distribution. And of course now we'll use the symbol S for standard deviation rather than the Greek letter sigma.